Series and summation. So you may remember from earlier in the year and from Algebra 1, we talked about arithmetic sequences and geometric sequences. An arithmetic sequence is formed by addition. A geometric sequence is formed by multiplication. So an example is 5, 7, 9, 11, 13, 15. You'll notice that there's a common difference, that every time we move forward, we add 2. This is an arithmetic sequence. When you add, or you could add a negative and subtract, the same thing as I progress in my sequence. A geometric sequence is one that is formed by multiplication, like 2, 6, 18, 54, 162. And again, as you move forward here, you're multiplying by 3. Now, a geometric sequence could also be formed by fractions. You'll see examples soon. For example, 1/2, 1/4, 1/8, 1/16, and so on. And every time I move forward, I'm multiplying by 1/2. Now, what makes a series different than a sequence is a series refers to I'm adding those numbers. So in an arithmetic series, it would be 5 plus 7 plus 9 plus 11 plus 13 plus 15. And we may add the first 20 terms or the first 25 terms. Sometimes in some sequences we may add an infinite number of terms. In a geometric sequence, if I turn that into a series, again, I'm adding these things. 2 plus 6 plus 18 plus 54 plus 162, and so on. Now, summation is the way the notation we use to write these series down. This is the Greek letter sigma. It's capital sigma. And the way it works is you can use some kind of variable like n or I, and I can say, well, I'm going to start at 1, and I'm going to do n squared, and I'm going to sum those, and I'm going to go to 5. So what this would be is 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared. And then I could work all those out and add them up, and that would be the answer to this question. So adding all these up, I get 55. Now, an arithmetic series, if I keep adding infinitely, will either go to positive infinity or negative infinity if I was adding a negative. A geometric series is said to either converge on a number, which means it approaches some number, and if I do it enough times, theoretically I would actually get to that number. For example, if I took 0.9 repeating, which is 0.9 plus 0.09 plus 0.009 plus 0.0009, and I kept going, this number actually approaches 1. Every time I add another 9 to my 0.9 repeating, I get closer and closer to 1. So that sequence would converge. It would converge on 1. The 1 would be the limit. That would be the final answer if I did it an infinite number of times. Now, a series can also diverge. Diverge means that it doesn't approach a sum. It goes to infinity. There are formulas to figure out some of these things. You could use spreadsheets and then just the brute force method to figure some of these things out. So before we get to some of the questions that approach infinity, here is just some practice with summation notation, seeing that you understand how it works. So the bottom number is the number you plug in. I'm starting at 2 here. You can start at 1, you could start at 0, you could start at 5, you could start at any number, but this question starts at 2. So this is -7 times 2, and remember that the Greek letter sigma means summation, so I'm going to add that, and then I'll plug in 3. -7 times 3, and then I'll keep going. -7 times 4 plus -7 times 5 plus -7 times 6 plus -7 times 7. So I started at 2, and I kept counting until I get to that top number, 7. And I keep plugging in those numbers until I get to 7. So 2, 3, 4, 5, 6, and 7 all got plugged into I. And because the Greek letter sigma means sum, I'm adding all those up. So you just punch this into the calculator and you got your answer. So summing these all together, we get -189. This next one is a real simple quadratic series. Quadratic because we're adding squares. That was like the example on the previous page. So I plug in the first number 1, and I do 1 squared. Then I plug in 2, 2 squared, and then I stop at 3. The top number is where I stop. So this is 1 plus 4 plus 9, which results in 14. Here's another example that's slightly more complex. So I'm going to start at 4, and I'll plug 4 in. -7 times 4 plus 7. Guess I'll use parentheses here. Then I'll plug in 5. -7 times 5 plus 7. And I'll plug in 6. -7 times 6 plus 7. And I'll plug in 7. -7 times 7 plus 7. And lastly, I'll stop at 8. I'll plug in 8 plus -7 times 8 plus 7. So again, I just work all these out and add them up. So this all adds to -175. In this next one, we're going to write this using sigma notation. And we're supposed to figure out what A is and what B is. Well, notice we're just adding the numbers 1, 2, 3, 4. So the last number will be 113. So that's where we're stopping. And this is the number we're plugging into. Well, this number here, it needs to be 1 for the first term, and 2 for the second term, and 3 for the first term. And notice it below, we're plugging in 1 first. So that is our n that we're plugging in, because that's our variable right there. So this should look like n equal 1, and I'm going to sum. I'm going to plug in n is my number I'm plugging in, and I'm going to stop at 113. So this is 1, and then I plug in 2, and then I plug in 3, and then 4, and I keep going until I get up to 113. So your A is n, and your A is 113, and your B is the n that you're plugging those numbers into. In this next example, there's a formula. It was discovered, as far as we know, by Carl Friedrich Gauss when he was 10 years old. His teacher gave the class some busy work, and the teacher said, all right, I want you to add up the numbers from 1 to 100. So I want you to go 1 plus 2 plus 3 plus 4 plus 5. Keep adding them all up. Plus 98 plus 99 plus 100. Well, Carl Friedrich Gauss looked at that. He thought there must be an easy way to do this. And what he did is he wrote the series down again backwards. 100 plus 99 plus 98 plus 97 plus 96 plus 3 plus 2 plus 1. And what he noticed is that if you add every pair here, every single time, those two numbers add to 101. So if you look at this list of numbers, there are 100 of them, from 1 to 100, and all those pairs add to 101. So if I take 100 times 101, what that would do is give me the sum of the numbers from 1 to 100 twice. So all I need to do then is divide it by 2. And this led to a formula that if I want to add the numbers from 1 to any number, let's call it n, I just take n times n plus 1 and divide it by 2. n plus 1 divided by 2. So in the example below, my n is 550. So I take 550 times n plus 1, so that would be 551. And then all I do is divide that by 2. n times n plus 1 divided by 2. Punch that into the calculator. Be careful, you need to multiply the top before you divide by 2. So the result of that is 151,525. Here's a quadratic series. Now, we could do this the brute force method, 1 squared plus 2 squared plus 3 squared, and I could keep going until I got to 10 squared. But, fortunately, there's a formula for this. The formula is the sum from, say, k equal 1, you can use any variable, of k squared to the number n is equal to n times n plus 1 times 2n plus 1 divided by 6. So this was discovered again by patterns, just like we did the last one. A little bit trickier though. But all you need to do here is know how to use the formula. So we're going to 10. So the formula says that'll be 10 times 10 plus 1 times 2 times 10 plus 1, all divided by 6. That ends up being 10 times 11 times 21, all divided by 6. Put that in the calculator. Make sure you multiply all the top before you divide by 6. And the result is 385. So the thing you should be wondering at this point is, how can I look at a sequence and know whether it converges or diverges? And we're talking about a geometric sequence here, which means that if this sequence is going to converge, it has to grow by multiplication. And the common ratio, let's remember what that is. We talked about this when we did exponential functions. Common ratio, it's equal to the current term divided by the previous term. So if the common ratio is less than 1, And our book uses R for ratio. Now, don't get confused here. We used R for rate previously, but we're going to use R for the common ratio. But if the common ratio is less than 1, and it would be the absolute value, if it's less than 1, then the thing will converge. So if the common ratio is greater than 1, it won't converge. It will go to infinity, meaning it will diverge. So if I take a term here, and I take the current divided by the previous, if I take 2 over 81 and divide it by 2 over 9, I'm going to use a calculator to do that. When you do that, make sure you put those in parentheses on the calculator. This ends up being 0.1 repeating. If you're using Desmos, when you type in the box, right to the left of the box, right next to the box, is a little fraction bar. And if you take that 0.1 repeating and hit that fraction bar, it'll turn into a fraction. So here the common ratio is 1/9. Now since that's less than 1, this sequence is approaching some number. So this thing will converge. Now it says if the series converges, find the sum. You need a formula for that. The sum of an infinite series is a sub 1, which is the first term, divided by 1 minus r, which is what our book uses for the common ratio. Again, they're not using r for rate as a percentage, they're using it for the common ratio. So in this question, our first term is 2/9, and we're going to divide that by, to find the sum of this series, 1 minus the common ratio, 1 minus 1/9. Now when you punch this in the calculator, be very careful. You're going to want parentheses around these things. And let's see what we get. Crazy as it seems, every time we go forward, we get closer and closer and closer to the number 1/4. So if I were to add that series up and do it an infinite number of times, I'm approaching 1/4, meaning the sum in infinity is 1/4. Here's another one. Is this series geometric is the question. Well, if it's geometric, then there'll be a common ratio. And remember, it's the current divided by the previous. That's negative 1/9 divided by the previous 1. So that would be negative 1/9. So just to check this, if I divide any two terms, do I get 1/9? I'll plug it in the calculator. And yes, when I divide negative 1 over 729 by 1 over 81, current divided by previous, I get 1/9. So this is a geometric series. It's a series because we're adding and subtracting. And there are formulas for that. You can make formulas that alternate the sign too by taking negative 1 to a power. Negative 1 to an odd power is negative. Negative 1 to an even power is positive. And this sum, because the common ratio, the absolute value of the common ratio is less than 1, this thing will approach some number. Every time I add a term, it gets closer and closer and closer to a number. So the formula was, again, the sum is equal to the first term divided by 1 minus the common ratio. So the first term is 1 over 1 minus the common ratio, negative 1/9. I'll put this in the calculator, and I get 0.9, which is 9/10. A couple more examples here. So this one's written in summation notation. It's an infinite series. Notice it's going to infinity. When we plug in 0, anything to the 0th power is 1. So this would be 1 plus. When I plug in 1, it'll be 1/7 to the first power, which is 1/7. When I plug in 2, it'll be 1/7 squared, which is 1/49. And I can keep going and going. You'll notice then as we go forward in the sequence, we multiply by 1/7. And if I look at current divided by previous, the common ratio is 1/7 divided by 1, or 1/7. So now I can use my formula. The sum is the very first term, which is 1, divided by 1 minus the common ratio, 1/7. Again, be careful when you punch that in. If you plug it in one line, you're going to need parentheses around the denominator. So I got a messy decimal, 1.16 repeating, only the 6 repeats, and I turned it back into a fraction, and I got 7/6. And this is geometric. Another example, if I plug in 0, anything to the 0th power is 1. When I plug in 1, I get 19/3. When I plug in 2, 19/3 squared, it's 361 divided by 9. And I can keep going. This is geometric because I'm multiplying by 19/3. Every time I go forward in the sequence, it's a power of 19/3. And every time I increase the power once, I multiply by 19/3 again. The question here, does this diverge or converge? Well, the common ratio, current divided by previous, is 19/3 divided by 1, which is 19/3. Notice how your R here is greater than 1, and it's the absolute value of R. It's greater than 1, so therefore this thing will diverge, meaning it doesn't converge on a single number. It goes to infinity. Last example. So this sequence, you can look at it and see that it is geometric. We are multiplying by 3/4 to go forward. 3 times 3 is 9, 4 times 4 is 16. Multiply the top by 3, you get 27. Multiply the bottom by 4, you get 64. So the common ratio is 3/4. Remember, it's current divided by previous, which is 3/4 divided by 1, or 3/4. So the sum of an infinite series is a sub 1 divided by 1 minus the common ratio. So the first term is 1 minus 3/4. Put this in the calculator. And the result is 4.